Greetings friends, today we are going to solve a problem from CodeChef August Lunchtime Challenge and the problem name is BNYHOPs. The problem code is BNYHOP. This is an easy medium level problem with two important prerequisites which are Eulerian tool and binary index tree. So let's move to the problem statement. There is a place which has n towns. These towns are numbered from 1 to n. This place is represented in the form of a directed tree such that all the paths are directed from the root and the root is town number 1. We are given an array P such that P of I is the parent of the town I plus 1 in the given tree, and we are also given another array A such that A of I is the rating of the ith town. What we can do is we can hop from town I to town j. But there are certain conditions that should be satisfied. The first condition is there should be either a path from town I to town j or a path from town j to town I. And the rating of town j should be lower than the rating of town I. That is, aj should be lesser than ai. And note that the array that we are given, A, has all the distinct values only. What we have to do is, we have to find the number of sequences of 2 or more towns that can be formed by hopping. Since the number of sequences can be very large, we need to report our answer modulo 10 to the power 9 plus 7. Let us have a look at the sample case so that we can understand the problem. In the sample, we have 3 nodes and we know that the node number 1 is going to be our root. And the parent of node number 2 is also node number 1 and the parent of node number 3 is also node number 1. And what are the rating of those nodes? The rating of node 1 is 10, rating of node 2 is 15 and the rating of node 3 is 5. I have represented it in the form of a tree. This is node 1, this is node 2 and this is node 3. Now we need to find Now we need to find the sequences of town that can be formed by hopping. One of the sequences, we can move from town 2 to town 1. It's possible because there is a path from first node to second node and the rating of first node is lesser than the rating of second node. Similarly, we can move from this node to this node. And there exists one more path which starts from node number 2, then goes to node number 1 and then goes to node number 3. Note that both of the conditions that were given in the problem are satisfied. And we can see that these are the only 3 possible sequences that can be formed. So the solution for this test case will be equal to 3. So let us have a look at the constraints for this problem. There can be at most 10 test cases, and in each test case we might have the value of n can be lesser than or equal to 10 to the power 5. The ratings of each node are value between 1 and 10 to the power 9, and note that all the ratings are distinct. It is guaranteed that the given graph will be a directed tree, and it is also said that the sum of n over all the test cases would not exceed 3 into 10 to the power 5. Since this was a lunchtime problem, there are multiple subtasks. In the first subtask, it's given that the given tree is a straight line, which means that there is this node 1, which is then connected to some node 2, which is then connected to some node 3, and so on. In the second subtask, it's given that the value of n is lesser than or equal to 10 to the power 3. And the third subtask has the following constraints of the problem. Next, we can move to the solution. But before moving to the solution, I would like to ask you to pause the video here and try to think the problem on your own. So let us consider that this is the tree which is given to us. Note that the values which are written inside the nodes are not the indices of these nodes. These are the ratings of the nodes. So what we can do is, in the given problem it was said that it's possible to move from node I to node j if there is a path from node I to node j or from node j to node I. And also the rating of node j should be lesser than the rating of node I. So here what we can do is, we can move from this node to this node. It's possible because the rating of this node is lesser than the rating of this node, and there exists a path from this node to this node. It is also possible to move from this node to this node because there exists a path from j to I and aj is lesser than ai. We can also move from this node to this node. It is because there exists a path from this node to this node, and that path is 10 to 1, then 1 to 8, and the rating of this node is lesser than the rating of this node. These are some other valid examples of sequences that are possible. We can move from this node to this node because the rating of the new node is lesser, and there exists a path from this node to this node. And also we can move from this node to this node because the rating of the newer node is lesser, and there exists a path from this I to this j, and that path is this. Similarly, for this case, we can move from this node to this node because the rating of the newer node is lesser, and then we can move from this node to this node because of the same reason. Also note that all the moves that we are making also satisfy the first condition. Similar is the case for the third test case. Let us try to make another observation, and this observation is that the sequence of the nodes that we are choosing should have the ratings in a decreasing order, as it is necessary for us to move from one node to another only if the rating of the newer node is lesser. So the path that we are going to choose should be such that the rating of the nodes should be in the descending order. It can be seen in this example also that the ratings are in descending order. First the rating is 9, then 8, and then 1. Similarly is the case for this case. The rating is first 8, then 4, and then 2. One more observation that we can make is that when it was said that we can move from node I to node j, if there exists a path from I to j, it indirectly means that we can move from any node to any other node which lies in its subtree, because there will always exist a path from a node to any given node in its subtree. For this example, there is this path from node 1 to node 2. Similarly, we can move from this node to any node in its subtree because there will always exist some path. So one observation is that we can move from I to j if j is in subtree of I. Next observation is based on the line where it was given that we can move from node I to node j if there is a path from j to I, which means I should be in the subtree of j, and this is the case only and only if j is an ancestor of I. Here we can see that it was possible for us to move from 8 to 4 only because 4 is an ancestor of 8. So we can move like this. And similarly is the case for this thing. We can move from this node to this node only because this node is an ancestor of this node. So these are the three observations that we have made. The first observation is that we can move only from a node to another node if the newer node has lesser rating, which means that the sequence of the node that we are going to choose must have the rating in descending order. The second is, if we are moving from node I to some node j, then j should either be in the subtree of I or j should be an ancestor of I. These two observations are very important for us. In this problem, we need to find the total number of moves. And many problems which require the total number of moves, total number of sequences, are actually dynamic programming problems. And this problem can also be solved by using the concept of dynamic programming. Let us try to solve this problem with the help of dynamic programming. Let us maintain a DP table where I define that DP of I is the number of ways that we can start from any node but end at node I after any number of moves. In other words, DP of I is going to be the number of ways such that we can end our moves at node I. So how can we find the value of DP of I? If we are at node I currently, in the previous step we should be in some node which is either in the subtree of I and which has rating greater than AI, or we should be at some node which is an ancestor of I and has a rating greater than I, or we can have another case where we are starting our journey at this node I. So our total DP relation will be this. We need to take the summation of DP values for all the nodes which lie in the subtree of I and have rating greater than AI, for all the nodes which are ancestor of I and have rating greater than AI, and also we need to add 1 because there is always a possibility that we can start at this particular node. One thing that we need to consider is the DP value of any node only depends on the DP value of those nodes that have rating greater than the current node. So when we are going to calculate the DP value for some node I, it is compulsory for us to calculate the DP values of all the nodes that have the rating greater than A of I. And if we are able to do that, we can easily find our solution by just trying to look in the subtree of I, by just trying to look in the ancestors of I. So how our solution will be is, we are going to process the DP table in the descending order of their ratings. And so when we are trying to find the DP value for some node, all the values which will have greater rating will already be processed and that DP values will already be stored. Another thing that will make our implementation easy is we can initialize our DP table by 0. And why would this thing make our job easy? Because then when we consider some subtree and all the nodes which have the ratings lesser than the current node should not be considered in our contribution. And since the value for them will be 0, so the contribution will not be taken. So it will be easier for us to initialize the DP value with zeros. So consider that we have got the DP values for each node. Now what will our solution be? For the given problem it was stated that it's possible for us to end at any node. So our solution must be summation of DP of I. But note that this summation of DP of I consists of all the paths which have only one node in them, because we have added 1 in our DP of I. And in the problem statement it was clearly mentioned that we should consider only the paths which have 2 or more nodes in them. So what we have to do is we have to just subtract n from this solution. So once we are able to find the DP table, we can give our solution by just giving the value of summation of DP of I minus n. Now how are we supposed to find the DP value? As I have already stated that we can process all the values in the descending order of the ratings. But once we are trying to find the DP value for some node I, what we can do is we have to know the summation of DP value of all the nodes in its subtree, and this thing can be easily done by using a DFS. We can use a DFS to traverse to the entire subtree of node I. Once that thing is done, we can have this value. After which we need to find the value of summation of DP of j for all the ancestors of I. And this thing can also easily be done because we are going to have the pointer to our parent. And what we can do is we can move to parent one by one unless we reach the node with index 1, because that node has no parent. And throughout the way what we can do is we can sum up the DP of j values. And then we need to just add 1. Now what will the time complexity of this approach be? So in total we need to process n values of our DP table. And in order to find the value of any DP of I, we might need to traverse an entire subtree, or we might need to go to the node 1, and this thing at worst case can be O of n. So the total time complexity might be O of n square. Note that this O of n square approach is sufficient if we need to solve the problem for our subtask number 2, and this thing will also be sufficient for our subtask number 1. But for our subtask number 3, the value of n was 10 to the power 5, and so the n square approach would give us a time limit exceeded. So now we need to find a better answer. Note that what we have to do in this case is we need to find the sum of all the values of dp which are in a particular subtree. This thing can be easily solved by knowing the concept of Euler tour and knowing some range query data structure like a segment tree or a binary index tree. Euler tour is a prerequisite for this problem, but still I am going to give a small idea of how making an Euler tour will help us to solve this problem. So Euler tour is nothing but the DFS tour of the given tree. But while we are making the DFS tour, one extra thing that we are going to store is the total number of nodes that we have traversed till now. So let's try to make the Euler tour for this given tree. Initially we will start over this node, so we'll give it 1. Then we'll go to its child, we'll give it 2. After which we'll go to its child, give it 3. Then we'll backtrack and then go to this child and give it 4. After which this, then backtrack, then this node. Then we'll go to this node, then we'll backtrack. Then we'll go to this node, backtrack, this node. Backtrack, 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 and then this node. So note that the value that we have stored over here are the total number of nodes that have already been visited in our DFS tool. How does this thing help us to make a query for any subtree? One observation that we can make is for any node, the order that we have stored, which is this value, the order of all the nodes which are in the subtree of this node are going to be in a range. As we can see, for this particular node, all the nodes in its subtree have the order 5, 6, 7, 8 and 9. This thing is a range. Similarly, if we try to find the order of all the nodes which lie in the subtree of 8, we are going to get 7, this 8 and this 9. So we can note that the order of all the nodes which lie in the subtree of a given node are going to lie in a particular range. This thing will help us because we can query and update ranges by using a few range data structures like segment tree and binary. We are going to process all the nodes in the decreasing order of their rating. And all the nodes that have been processed will have the DP values. And for all the nodes that are not processed, the DP values are going to be 0. Now, when we need to query and find the sum of dpj values for all the values in the subtree of I, since that thing is required for us to find our value here, that thing can be easily done by the concept of Euler tool and a range data structure. This is because after finding the value of any node, what we are going to do is, in a segment tree or in a binary index tree, we at the index of order of this node, which is when we are going to find the value for 1 for this node, at index number 4, I am going to store its DP value. And now, next time if I am going to find the answer for this node, if I try to find the sum from range number 3 to range number 9, so if we can query the sum of this range easily, indirectly we are going to query the value of DP of this entire subtree. In this way, we are going to solve the problem. But still our solution is not complete. We have found a way to fasten up this part of our transition. But still this part, where we have to traverse through all the ancestors, is still going to take, in the worst case, O of n time. And this would be the reason that our time complexity would still remain O of n squared. Now we have to find a way so that we can fasten up the summation of these values. So the part that we have to consider now is, when we are trying to find the DP value of this ith node, we also need to find the summation of DP values of all its ancestors. And the nodes which have the AJ value as lesser than AI will have the DP values as 0. so they are not going to contribute to our answer. So how can we find the sum of DP values of all the nodes which are ancestor of the given node? It's not possible for us because there is no pattern, but one observation that we can make is as soon as we are going to find the DP value of some node, we know that all the values which lie in the subtree of that node are going to have the contribution of this node, because this node is going to be the ancestor of those nodes. Let us take an example. Consider that I have found the DP value of this node. After which, when I am trying to find the DP value for this node, since 1 is an ancestor of this node, I need to add this contribution. Similarly, if I am trying to find the DP value for this node, still this thing is an ancestor, so still I need to find the contribution. And so for all the nodes which lie in its subtree, this DP value is going to contribute to that DP value. So what can we do is, as soon as we have found the DP value for this node, isn't it favorable for us to update the DP value for all the nodes in this subtree by this DP value? Because however, when we are going to find the DP value for this node, we are going to consider the contribution of this node. So why not, as soon as we have found the DP value for this node, we give its contribution to all the nodes in its subtree. In other words, all the nodes in the subtree are still going to be lying in a range, that is for this node. All the nodes in its subtree are from range 5, 6, 7, 8 and 9. So what we have to do is, in an entire range, we need to add the contribution of this DP, which will be DP of I. In other words, we need to make a range update. And we have many data structures like a segment tree or binary index tree which support both range update and range query. We need range update for this, and we needed range query so that we can query the summation of all the values from the subtree of a node. So with the help of Euler tool and a good range data structure, we can find the DP value for any node. And as soon as we find the DP value for any node, we can give our answer by summation of DP of I minus n. Let us try to have a look at how are we planning to implement our solution. In order to implement our solution, first we need to sort the given array on the basis of the rating. Once we have sorted the given array on the basis of our rating, now we can process this array from backside and we can maintain our DP table. For this solution, we also need to have the Euler tool. So first we can make an Euler tool and create this array which will be called as rank. Now for any given node, how are we going to know the range of the nodes that will lie in its subtree? It can be easily found, because if the rank of a given node is R, the range in which the rank of the nodes in its subtree will lie are going to be R plus 1 to R plus size of this node minus 1. Well, what is the size of this node? It's the size of the subtree of this node. It can be easily seen that for this given node, what are the 3 nodes that are in its subtree? They are 7, 8 and 9. And what will this thing give? It will be R plus 1 to R plus size minus 1. And what is size? Size is 3. So it will be R plus 1 to 7 plus 3 minus 1, which is 9. So it will be 7, 8 and 9. So for a given node, how can we find the set of all the nodes which will lie in its subtree? They will be from R plus 1 to R plus size minus 1. For this problem, we can use 2 binary index trees. First binary index tree will be used so that we can query from any range, and the second binary index tree will be used so that we can update the DP values of any range. Here consider that we are finding the DP value for this node. Now since for all the nodes which will have their AJ value greater than this AI and which are ancestor of these nodes, they were already processed, so their updates are already made, and so the value that we can get from this node will be equal to the value that will be contributed by its ancestors. And then how can we get the value that will be contributed from its subtree? That can be easily found querying the range r plus 1 to r plus size minus 1 over here. Once we find the contribution from this range and we already have the contribution from ancestors, we can easily find the dp of I to be equal to the contribution from subtree plus contribution from ancestor plus 1. But now when we have found the dp value for this node, we also need to update the entire range from r plus 1 to r plus size minus 1 by this value. We need to add this value into that range. How can we do that? In order to make range updates in a binary index tree, what we can do is we can add dp of I at r plus 1 and we can subtract dp of I from r plus size minus 1. From r plus size. And once this thing is done, if we need to find the dp value at some particular node, it can be easily found by taking the prefix sum. This is the concept that is used in order to make range updates in binary index tree, and that is a prerequisite for this problem. So in this way we can find the dp of I for any node, and after finding the dp of I, we can update our binary index tree. In such way, after finding all the value of dp of I, we can find the summation of dp of I, and from this value when we subtract n, we get our solution. Next we can code our solution. Let n be the total number of nodes and here G is the adjacency list of the given tree. We have two other arrays which are rank and size. Rank array stores the rank of each node after Euler tool is applied, and size array stores the size of each subtree. After this thing is done, we take our number of nodes and then we take the parent of each node, and here we are creating the adjacency list. After which we need to take the rating of each node. We store the rating of each node in an array of pairs. This array of pairs consists of rating, comma index. After which we apply this DFS of 0. This DFS of 0 is used to make the Euler tool. Here this is a simple code which does the Euler tool. After this Euler tool is over, we have our two arrays, rank and size. Rank array consists of rank of the node and size array consists of the size of the subtree of this node. After which we have sorted our array A. So this array is sorted on the basis of the rating. We are going to maintain two binary index tree, one binary index tree so that we can take the query from the subtree, and one binary index tree so that we can take the updates that were made by our ancestors. After which we have to iterate through the sorted array from n-1 to 0 so that we can iterate in the descending order. Now V will be the index of the node. dp value is what we have to find for this node. Initially the dp value will be the sum of dp values of its subtree, which can be easily found by taking this range update, this range query. Query.sum from rank of V to rank of V plus size of V. After that, we need to take into consideration the contributions that are made by our ancestors, and that thing can be easily found by this thing. Taking dp value plus equal to, in update binary index tree, we will take the prefix sum till rank of V, and after which we need to add 1 to our dp value. Then we can add this value to our answer. Now we have to update all the binary index trees. In this query binary index tree, we need to make a point update. We need to make point update at this index, and the new value is dp value. After which we need to make a range update in this binary index tree. And making a range update in binary index tree can be done by adding this value at rank of V index and then subtracting this value at this particular index. This particular procedure of updating in a binary index tree and then querying one particular point from a binary index tree is a very well-known method. And after all of these notes are processed, our solution will be stored in answer. But note that we need to subtract n from our answer. After we subtract n from our answer, we can print our answer. Now let us try to run our solution. As we can see that our solution has passed all the sample cases. Now we will try to submit our code. Now we have to wait for the result. We can see that our solution has got accepted. Thank you.